Okay, let's start. Hello, everyone. So today our topic is about gene set enrichment analysis, theory and application. So basically, the GSEA part will be split into two videos. First is the theory and application introduction, and second is introduction of hands-on application. So let's start from the background of pathway and gene set enrichment analysis. Here I give a definition. So the goal is of pathway enrichment analysis or gene set enrichment analysis is for a given gene list A, like for example, like upregulated genes in colon cancer versus normal, that identified from a certain gene list B, like all the measured gene expression, and denotes the number of genes in A as n. There are n, so the number of genes in A is n, and to determine if A is more enriched to certain pathways or gene sets compared to randomly drawing n genes from B. So, and here I give an example for better understanding. I give an example about the classic hypergeometric or similar contingency table-based test, which we have learned from other videos. So like shown here, so in total we have 10,000 measured genes. And among the 10,000, 1,000 genes is identified as in A, for example, upregulated genes, and 9,000 are identified as not upregulated genes. And for a given pathway, there are 200 genes in this pathway, and 9,900 genes are not in the pathway. And for example of this observation, we have 100 genes in A that also are also identified as in the pathway. And also 100 genes in the pathway are also identified not in A. So we have in the pathway, the proportion of genes in A and not in A is 50% and 50%. And on the other hand, for the genes not in the pathway, we found that 900 genes are in A, but 8,900 genes are not in A. So this figure shows basically shows the list, shows the ratio. And from this, we can see that the genes in A are more enriched to the pathway, we can see. Or the pathway are more enriched, or the pathway are more enriched by the genes in A. Or the pathway is more, for example, if A is upregulated genes, here the pathway is more enriched by the upregulated genes in A. And basically, the hypergeometric, you might have learned that the hypergeometric test can test the statistical significance of such contingency table-based statistics. But for some case, so we may consider, so other than the cons, so currently, for example, if A is upregulated genes, there's no information of how the upregulation of each gene is used in computing this pathway enrichment or gene set enrichment. For example, in cancer data, a common observation is that the cell cycle genes are among the top overexpressed genes in cancer versus normal. And some metabolism genes or mitochondria genes may be slightly upregulated in cancer versus normal. However, the proportion of the genes, of the cell cycle genes that upregulated the cell cycle genes in cell cycle pathway may be similar to the proportion of the genes, the upregulated genes in the mitochondria pathway. Even they are all both upregulated. If we just use the counts, number of upregulated genes as the input, we may consider these two pathways may be similarly upregulated. However, when we consider the level of differential expression, we may say, okay, cell cycle may be more upregulated. So with this idea, so people developed the GSEA gene set enrichment analysis with considering the level of differentially expressed genes. So here is we just use a real data example to illustrate the approach of gene set enrichment analysis and to illustrate the underlying theory. So for example, we have 8 samples measured of gene expression data, measured of 8 samples with 4 wild type, 4 knockdown of certain gene. So here we have use 0 to label the 4 samples that are with wild type condition, and for 1 label the samples just as an indicator of the samples with the knockdown condition. And then what we can compute is we can first compute this is then we go for the exact approach used in GSEA. So we first compute the correlation between gene expression and each condition and each condition. So actually the conditions. So here we can see for the first gene we can compute the correlation. And then the correlation is shown here. This is the basic R code. So we give for the condition as 0, 0, 0, 0, 1, 1, 1, and the correlation condition with data. And also definitely we remove the data with too many zeros or too less number of non-zero observations. And here is the correlation we identified. So for example, like this gene, SLC1A5, it shows very strong negative correlation with the condition. We go for here, we can, is this in the top? Yes, here we go. So you see, in the wild type group, most of those genes, all the four samples, the expression level is about 5, and in the knockdown group, it's all about 3 point what. So we can see a significant downregulation here, and this correlation can reflect the upregulation or downregulation. A negative value means downregulation in KD, in knockdown, and a strong positive value means upregulation. Then we use 20 genes as an example. For example, there are only 20 genes observed in this experiment. We just observed 20 genes in our gene expression data. And for a pathway and then here are the 20 genes with the correlation computed. And then we sort the correlations by the descending order. So we have these genes with the highest correlation, these genes with the SLC1A5 with the lowest correlation. And for example of pathways of 3 genes, for example, for pathways of 3 genes of GTF2IRD2 and MIRA 4252 and CCSER1, if we have the pathway of these 3 genes, we can say, okay, this pathway is definitely enriched by the upregulated genes, more upregulated genes in this data. Because you see, for this pathway, we see these pathways are the genes from this pathway are all the top 3 positively correlated genes. The genes positively correlated with the knockdown condition. That means this pathway is upregulated in knockdown versus control. And similarly, if we have the genes, pathways formed by the genes PLBD2 and RFXANK and SLCA5, if this is a pathway, and when we say, okay, these 3 genes are about the top negative correlated genes with a knockdown. That means the top downregulated genes in the knockdown condition. So we can say, okay, this pathway is downregulated. And for a pathway like for these 3 genes, they're just more likely randomly distributed. So okay, we may consider they are not insignificantly differentially expressed. So with this idea, we can think we got with this toy model. So we get an intuitive idea, which is that if after you sort the correlations derived by correlating the gene expression versus the conditions, the pathways that are with the genes enriched in the top part of the gene list that are more likely upregulated genes, and the pathways more enriched by the lower part or bottom part of the genes, which are enriched by the genes with negative correlations, are more likely to be downregulated. So with this idea, GSEA is developed by using just a mathematical or statistical approach to quantify the level of the enrichment of the genes to the upregulation part and downregulation part. And more importantly is you can see here, for example, GTF2IRD2 is with a 0.89 correlation, and the MIRA 4252 is with 0.3 correlation. That means this can suggest the first gene is more upregulated compared to the second gene. So in this table, in this list, the level of differentially expressed genes is also encoded in this data. we didn't lose the information, the information of the differential expression level. So, and here on the right, I showed the approach of the GSEA. So start from an enrichment score ES equal to 0. So GSEA just screen for each pathway. GSEA screen from the top to the down to the bottom part of the list of the correlation. If hit a gene in the pathway, for example, if the pathway is this formed by these three genes, ES will add will plus or add a value to the current ES. And if you hit a gene not in the pathway, will minus a unhit score to the from the ES. So we see here the S hit is defined by the sum of the pathway, all the genes from the pathway, the absolute value of the correlation, and with to the power of alpha. Alpha is tuning parameter. So for example here, so we have the correlation is if we put set alpha as 1, which is a very common setting. So the S hit of the first, if the pathway is formed by these three genes, the S hit equal to what? Equal to the sum of these three. Is a level, the correlation level divided by the sum of this three correlation is a 0.584. And similarly, we can get the S hit of mirror is 0.22, and the S hit CCS ER1 is 0.196. So then we may sum it. So we may do the when the ES, then when we go run the GSEA, it screens through the top to the bottom part. First, the score will ES will add by 0.584. Then hit the second one, continue add 0.22, and then continue add 0.196, and then they will reach 1, and then all the rest are unhit. Unhit is defined by the 1 divided by the number of genes not in the pathway. So we can say the ES, the sum of the, by this definition, the sum of S hit is 1. The sum of S unhit is 1. So when I go through this, so what will happen is that at the end, the SES score will become 0. But if this is this gene, the pathway is enriched to the top part of the gene list, what will happen is that the ES will continue grow, tends to continue grow and growing, and then start dropping. It's like because the pathway is more enriched by the genes in the top part. And reversely, so if the pathway is more enriched to the bottom part, so you can say when we run the GSEA, the beginning hits are all unhit, so we'll keep minus things, minus this as unhit value. So we minus, and then the ES score will go for negative, and then start to add to become to add more positive values, and then go to 0. So then this may result. So based on this formulation, so if we see the trajectory of the ES for different pathways over the same rate list, we can see, for example, if the pathway is enriched by the front part, by the top part, and this is the ES level at when we screen different number of genes, we see the ES will start to grow, and then drop. So the grow means that the hit of the genes in the pathway. And also, by the definition here, the higher value of the correlation may give a higher S hit score. So in the beginning, if they meet like more upregulated genes, they will grow more or faster. And then in the further part, if they meet a kind of a gene that not so significantly upregulated, the race will be not that high. So you see here, the first race will be very high, but later race will be relatively slight. So this is how GSEA works, and this is the typical curve that we will achieve for an upregulated gene list. And this is a typical one we will observe for insignificantly differentially expressed genes. You can see the growth, the hit are just more likely randomly distributed through all the genes. And this is more like you can see here, the genes is in the beginning is upregulated, and then in a region they get sudden increase and then decrease. This is more like a genes that more like a pathway that are enriched to the unchanged gene list. This is also happen. It's more like unchanged. So once we observe this type, we may consider, okay, this even the ES score, the highest level of ES score is still high, it's still distinct, but this may be more like the insignificant, enriched to an insignificant differentially expressed case. And also, oh yeah, one thing is that once we get this curve, the highest value or the lowest value, the highest value is of the ES curve is considered as the enrichment score of the upregulation, and the lowest value is considered as the enrichment score of the downregulation. So this is a typical observed score, ES score that of a downregulated pathway. So you can, I believe you have seen this type of figure multiple times in your when you read the other papers. So basically, to read this is the trajectory of the ES, and this is the ES, the enrichment score's lowest level. And once you see this pattern, this may tell you, okay, this gene is more likely to be downregulated. And once you see this pattern, the one gene is more likely to be upregulated. And here is the color bar here shows just the level of the correlation that you used for in computing the ES score. So here the more red means higher correlation, more blue means darker blue means negative correlation. And each of the bar, the segment here just may indicate the hit of a certain gene in the pathway. And here is these two examples are just two examples of upregulated genes, upregulated pathway and downregulated pathway. So please note here that, so for all the pathways, you will run, for each of the pathways, you will run one time of the analysis just by the approach screening through the top to the bottom of this correlation list. And you will get one of this figure. And then, and also, this plot just shows the trend, but for all the analysis, we want statistical significance. So what I can tell is that the GSEA basically is use a permutation test permutation-based test. What that means is that once you get a certain pathway, they may just one way is they may permute on the pathway side. Is randomly draw certain number of genes, the same number of genes from the list, and compute the ES score and test and do it 1,000 times or 10,000 times, and then see how many times of the randomly drawn how many times of the ES score from the randomly drawn pathway with the same pathway size that is above the ES score or lower than the ES score that can derive a p-value. And second time is permutation, is permuting the samples. So this is may lower the computation. So basically they may permute the sample order just by recompute the correlations. For example, just shuffle the order. For example, give this to WT, this to KD, and this to WT, this to KD. Just randomly shuffle the samples and then recompute the correlation and recompute the ES score. And that can also be used as a background empirical distribution, so to assess the p-value. Okay, so that's basically all the theoretical part of the GSEA. And currently, so I recommend this two application approach to the people who are not from the programming background or computational background. One is the GSEA Java version. So it's a user-friendly Java version, can enable you to upload certain gene, the data and gene list with a certain format that to execute the whole GSEA approach. And second is another web server is called the Gestalt's web server. So this is a web-based gene set analysis toolkit. So they are include on this web server. They include multiple gene set enrichment computational method, and with the GSEA, the input is not, instead of the original data and conditions, they require to include this list, the list of the the level of just a scalar value to represent the level of differential expression of each gene to upload this vector. And in the next lecture, I will introduce the hands-on part of the GSEA Java version and this web server. And also the last thing, please keep in mind is that there are multiple methods to compute this the value that or the level of differential expression test. For example, you can use log fold change, you can use correlation, you can use the t-test statistics or other statistics. And this is a lot of classic measurements were available in the GSEA Java version, and which we will talk about in the next video, next lecture. Thank you.